So we have learned up to this point that clearly metals have different abilities to oxidize. We looked at net potential tables. We looked at that condensed table called Table J. We looked at its Table J in terms of metals and nonmetals. Looked at who oxidizes best and who reduces best, and understand that those differences result from a pathway, a thermodynamic favored pathway. If a reaction works, we should understand that it gives us positive volts. That means the one who's throwing its electrons can do so and force them on the other one. Or it means, which would be the one who oxidizes, also means the one who is reducing could pull electrons away from the one who's oxidizing. You can look at it from both perspectives. I'll say that again. If a reaction is spontaneous, and we've looked at them through different ways in different homework examples, you have to do them for me. We can think that a redox reaction occurs, and this is important for today, because the one who oxidizes can force its electrons onto the one who's reducing. That's why we call that one who oxidizes a reducing agent. It can force the reduction. Or the one who's reducing can pull the electrons away from the one who's oxidizing. That's why we call the one who reduces, gains electrons, the oxidizing agent. So if the one who oxidizes or reduced is strong enough to cause a transfer of electrons, we will get positive volts. If it's not, you get negative volts and the reaction is non-spontaneous, which means it doesn't work. Case in point. Okay? I'm not sure if you're aware of this, but around 1980 or so, the price of copper that pennies were made out of increased so much that the actual price in weight of the copper in a penny was worth more than 1 cent. And that was a problem. Okay? So we had pennies out there in the 1980 or 1979 that were worth more in their weight of copper because the price of copper had shot up than the actual value that the federal government gave this piece of metal. That was a problem. We didn't want people to gather the copper coins, melt them down, and sell them as scrap metal. So what they did after 1981 or 1980, which is post-1980, is they made the pennies a little differently. So I have a 1975 penny up here. That's the old way. It's pure copper. Okay? Now how do I know and how can I tell you it's pure copper? Well, because you know the color of copper because we just did a lab. So if I take a 1970 penny and I just take a file and I just scratch, boy that's blurry. If I just scratch the end of it, all you're going to get is another, what? Copper color. Okay? Now, if I move the 1970, whatever, older penny away, and now I do a new penny. This penny is 2011. So this is a post-2000, 1980 penny. This is the newer style. These newer pennies, so they're not worth more than 1 cent in their weight of copper, have a very tiny thin skin of copper. On the inside is zinc. Now from our lab, what color does zinc have? It's got like a silver color to it, sure. So all I'm going to do is I'm going to just scrape off the side of the copper penny. And you're going to see that I'm going to expose, oh, I can do this. I can expose the zinc. Here we go. Can you see that? I don't know if it is here or it's really hard to do. Can you see it? Can you see that? I can't go there we go. No, can you see that's got a silver color to it? Okay. So that's the zinc core. I'm going to do it to the other side. My cuticles need work, I understand. I haven't manscaped in a while. Yeah, I feel embarrassed. Okay. They didn't look bad until I saw them that close. Okay, now listen, here's what I've done. I've exposed what? The zinc on both sides. Now what do we know from a reactivity series? What do we know? Will copper react with H pluses? The answer is no. Why? Why won't it react? Source this out. Let's go back to our net potential table. Go back to table J, or this table. We'll stay right here. We'll stay right here. Okay, look what I have here. Oh, my glasses on my head, I didn't even know that. What do I have? I have copper, who's too low. Let's bring this up. Where's copper? Copper, for it to oxidize, right? To get positive volts, right? For it to oxidize, what's the charge here? Going this way. Negative. I need something positive enough to force it to what? To become positive. So where's H pluses? Above it. What this means, and this is what we do in AP chemistry, H pluses are not strong enough to pull electrons away from the copper. Because if you do the voltage, 0 plus a negative 3.4, it doesn't work. So when I drop H pluses from hydrochloric acid onto my penny, the copper will not react. Well, what about the zinc? The zinc is right here, believe it or not. What about the zinc? Will the zinc work? Yeah, the zinc is way above. So the zinc oxidizes, it's positive 0.76. This is the right angle. So the zinc will react. So what I'm going to do, party people, is drop hydrochloric acid onto this penny. Remember, this penny has what? Both the, oops, source it out, sorry, my bad. So what I'm going to do here, because I've exposed the what? The zinc on one side and the zinc on the other, I'm going to put it in a dish and I'm going to drop some acid on it. Now, what do you think you're going to see? What do you think when I drop H pluses on this metal? What did we do in this lab? What did we do? Is the copper going to react? What's going to react? Right. The zinc 0 is going to oxidize with the HCl to make what? Zinc chloride and hydrogen gas. We're going to see bubblage, people. And where is the bubblage going to occur? The sides. So I'm going to use concentrated hydrochloric acid so I can increase this. It may not be done at the end, but by tomorrow what we'll have is a penny that should be just hollowed out. All the zinc will become zinc chloride, okay, and the copper will remain. That's why, guys, we use copper what? Pipes. Any acidity in our pipes, the copper resists. One of the reasons why copper is expensive. Metals that resist corrosion typically are more expensive. All right, now, so using concentrated acid, I'm just going to pour some. And where is our fizzing occurring? On the sides where the what's exposed? Where the zinc is exposed. So clearly, you can clearly see that where the zinc is exposed is right here and right here. And the H pluses are doing what? Pulling the electrons away from the zinc. The zinc is becoming zinc plus 2 and it's going into solution. Okay? The copper is not reacting. The H plus is not a strong enough what agent? It's going to force zinc to oxidize. It wants to model. I'm a modeling agent. H plus is not a strong enough oxidizing agent. Okay? All right. So that's going to sit there and do that magic for a little while until all the zinc, okay, is reacting. We should have a hollowed out, thin little shell piece of penny. Okay, I'm going to put that to the side. Now, I'm going to do a different demo now. You may say to me, well, how does zinc react? Is there something that will react with zinc? Yes, there is. Okay, I can't use the H pluses from HCl, but I can use something called the nitrate ion from nitric acid. The nitrate ion is strong enough. So here is the next demo. Okay, in this flask, I'm going to put copper pieces. Boy, I think my camera has seen better days. All right, but, okay, so what I'm going to put in this flask is pure copper. Okay, now we know pieces of copper are resistant to H pluses. I need a strong enough oxidizing agent, so let me cut some copper up. Okay, we'll finish this demo. So some pieces of copper, a little bit oxidized, but it doesn't matter. Now I could put copper pennies in here too, but I don't want the AFTA to get me. They probably should get me for that 1 penny I'm destroying right now. Bless it. Okay, so I got some pieces of copper. Crease the surface there a little bit. Okay, now I'm going to take this copper, and obviously we know it's not going to react an acid. We already saw that in lab. So I'm going to put this copper into this Florence flask. If you think it was pre-recorded, now you know it's not. Okay? That was a joke. Okay? Now how you really know it's not pre-recorded? This wouldn't happen in a timely fashion. Okay. Now, fill that up with copper, why not? Now, I'm going to need a strong oxidizing agent. So copper is down here in table. I need something who's going to reduce to be below it. And Au ions, not Au, I'm going to use nitric acid. It's not the H pluses, it's the NO3 minus. We'll talk about this in AP, but I want to show you the reaction. So I'm going to add nitric acid. Now it's not the H pluses that are going to do the action, it's the NO3 minus. So let's do this. Now, what I'm going to do, this is a pretty cool reaction. It's actually very exothermic, but I'm going to drop some acid on here, nitric acid, and it's not the H plus. Now, for those that don't know what nitric acid is, and that'd probably be all of you, nitric acid is HNO3. It's going to dissociate to H plus, which has no effect, to NO3 minus. This is a strong oxidizing agent, stronger than H plus. So it's below copper, okay, if you can think of it that way. Here we go. So here comes some nitric acid, and it makes a noxious gas. That's why I'm in the fume hood. Now, for those that want to see what's going on, okay, I'm boiling. The gas being made is pushing the gas into this flask, yeah? Too much pressure. Wow. That won't stay. It's coming out too hot. Let some of that relieve. Now what's happening is so much gas being produced that's pushing the top off. And I never had this issue before. Well, we'll just do that. Hold on. I'll just hold it. Okay, so you saw a brown gas, and that brown gas represented NO2 gas, a noxious gas. Now, what's happening is the gas is being generated. Now, heat was given off. Now, the deal here is that once the reaction stops, and it looks like for the most part it's done, once the flask cools, it's going to create a vacuum and pull the water back. Except this isn't working the way I'd like it to. All right, so what I'm going to do is just pour water into it. Okay, so I'm going to take this flask and I'll pour some water into it. So you can still see that it's reacting. Okay, and this is not a brown flask, this is full of NO2 gas. Okay, now I'm going to pour water in this. It's still going. The reaction's almost over. Okay, but without time, I'm going to pour this back. Now, by pouring water, I'm going to force the gas out. The pure copper, what does copper look like when it's ions? Anyone know? Have we dealt with copper ions before? Let's see. What colors are copper ions, remember? The blue-green, right. Okay. So our solution here should be a little bit green. In fact, it looks like to me that we didn't get all of the copper reacted. So I'm going to add some more acid here. And now we can see what's happening. Everyone see the color now? You can see the nice blue color, and the acid is decaying into copper ions. So as that reacts, this will get much bluer as more copper ions are being emitted. Copper 0. What's happening here, guys? Copper 0 is being oxidized or reduced. Being oxidized by the nitrate ion, and it's becoming copper plus 2. And what happens is this N. Now, what's the charge of the nitrate ion? The whole thing equals negative what? 1. So this is negative 2 for the oxygen, negative 6 overall. What charge must be the nitrogen if it's negative 1 overall? Plus 5. Very good. So each nitrogen is plus 5. Now, we make NO2 gas. That's that red gas. Watch. What's the charge on that? Negative 2 individually for the oxygen, negative 4 overall. What must be the charge of the N if the whole thing is 0? Plus 4, right. So what's actually being reduced? N plus 5 goes to N plus 4. And that's what that red gas is. And you can see that I'm eating away the copper, okay, by the nitrate ion. The nitrate ion is pulling electrons from the copper and making it. This is important. This is important for today. Solid copper. Anytime copper is 0, anytime any metal is 0 with the exception of mercury, it's a solid. And this has to be important. If you make what? Aqueous copper. If it dissolves, it has a charge. So what's happening is the mass of the solid is decreasing because it's going into what? It's becoming copper plus 2 here. So solid copper 0 is becoming copper plus 2. What's happening to the mass of the solid copper as it becomes copper plus 2? What's happening to the amount of solid copper as this reaction goes to the right? It's decreasing. What's happening to the amount of ions? Increasing. Okay, good. All right. So this brings me to the next piece, okay, which is now going to be called Daniell cells, or we say Voltaic cells. And let me give you a little story, okay? There was 2 scientists in an argument. The argument was very simple. Luigi Galvani was a biologist. Okay, this is 100 plus years ago. Now, what he was doing 150 plus years ago, something along those lines, he was taking frog legs, live frogs, or pith frogs, something in between. Okay, so fresh frog legs, okay? And he was basically taking static electricity and hitting the frog legs with static electricity and watching the frog legs twitch. In his eye, electricity, which was a newfangled thing at the time, it didn't really understand the laws and it wasn't fully explained, obviously. His idea, electricity, was inherent with biology. Biology made and controlled electricity. It was a biological event, according to Luigi Galvani. Now, in the same country, they're both Italians, there's a guy named Alessandro Volta. He was more of a physical science person. He was like, that's hogwash. Biology is just using the laws of nature to do something. Luigi Galvani says, well, you're hogwash, okay? I'm not sure what that means, but you wash yourself with hogs, maybe. But the point being is that to prove it, Alexander Volta built himself a battery out of non-living things. Basically, it was silver and copper, I believe, with pieces of salty paper in between, which we'll talk about. And he built a battery that created a voltage. And he took his battery, which was a non-living pile of metal, that's why they call it the voltaic pile, took the 2 electrodes, 2 wires, and he zapped the frog legs and they twitched. And Luigi Galvani conceded. Because of these 2 people, they call a battery now either a galvanic cell, because Galvani was the first to start the argument, or a voltaic cell. You'll hear of a galvanometer and a voltmeter interchangeably sometimes because of the 2 people involved. So a galvanic cell and a voltaic cell are both for batteries. Okay, so what we have here is a battery. Now a battery is an application, okay, of redox that we learned. I want to build this, call it Danielle cell. I'm going to take a zinc solution, okay? Let's take the camera off this because I don't think we need to see that anymore, but over time that copper will become solid, will disappear. Okay, so I'm going to take this, maybe set up over here. Okay, ooh, Christmas in July. I'll take that. Okay, so that's our cell. So I'm trying to set this up here. Now I have my zinc solution, which you can see is colorless because it's not a transitional. You see my copper solution, which has that greenish blue tinge. And we'll do it like that. All right. Now, I am going to put up a voltmeter for Alessandro Volta. Hey. Okay. Now, I'm going to put him here. Now, with every battery, we need 2 electrodes. Electrodes are places where the redox reaction occurs. So, we're going to use 2 metals in this course all the time. There could be other things, but in this case, I have my copper. Everyone knows what copper looks like. The copper is going to go in the copper nitrate solution as I'm pointing. And then I'm going to put my zinc, which goes in the zinc nitrate solution. So those are my 2 metals, hanging out, chilling. Okay? Now, what I'm going to do is explain what's going on. Right now I have 0 volts. What does that mean? Is there any potential difference? What's a voltage? A voltage is a force that pushes the charge around. Right now there's no force in its meter because nothing's connected. Okay, but I will in a second. Let's break down what's happening here. Okay, so let's take our, and I want you to write this. You have this one somewhere. Okay, so let's do this. Or just watch. Here we go. Now, the absolute first step I have here, party people, is that I have 2 metals. This is the absolute first starting place in any time you look at a voltaic cell. You must evaluate who your electrodes are. We have 2 electrodes. Who is better at oxidizing? Zinc or copper? Think of your lab, people. Who is higher on table J? This is zinc, and this is copper. Who is better at oxidizing? Zinc. Zinc is better at oxidizing. For those that do not know, you go to table J, and you'll physically see that what? Zinc is higher. You guys should know this from your lab. So the absolute first step is you go to your table J, and you go see that what? Zinc is higher than copper. I don't know if we can see that here, okay? But you can see that the zinc, which is, where are you, ZN? Right there, my finger is higher than the copper. Okay? Now, what does that tell me? Most important piece of information. Knowing that zinc oxidizes best, it's screaming to me that this side is oxidation. So this is the oxidation side. My friends in chemistry, what does a battery do? Doesn't it provide a current? Yes. It produces what? Energy to run your phone that you might be texting on now. okay, or your anything else. A battery produces energy. The energy comes from the voltage. It comes from electrons being passed around. My friends in chemistry, if I separate who gives off electrons from the one who gains, couldn't I pass that along a wire? The answer is yes. I'm separating the redox reaction. That's what I'm doing here. Now, pay attention. The copper is not as good at oxidizing, so we'll say this is the reduction side. This is the side that gains electron. The stuff that we learned is still here, party people. We have the what on this side? The Leo. This side is losing electrons. This side is gaining electrons. And if you can see with me, where is the electrons going to flow? What do you think? Just use your logic. Where would it flow? From the what side to the what side? From the place that loses electrons to the place that what? Accepts. So electrons are always going to flow from the oxidation cell. So I want you to draw arrows along this wire. Now let's get into the specifics. We start with the two electrodes. The first step, figure out who's better at oxidizing. The one who's better at oxidizing, that becomes the place of oxidation, and we have a specific name for it. We have Leo the lion. Now we have another mnemonic. We call it anox red cat. So here's the anox, and here's the red cat. Now what does that mean? That means the anode is the electrode where oxidation occurs. That means that the cathode is the place of reduction. So where do electrons flow from? The cathode to the anode, or the anode to the cathode? Anode. The anode of your car battery. If you look at your car battery, your folks' car battery, you will see there's a little negative sign next to the anode. We put a negative sign there just by convention to say that's the place where electrons are coming from. Forget this, sorry. Arrows are going always from the end of the cathode. Just by convention, I put a positive sign for the cathode, and that's where electrons are traveling to. When you look at a battery, okay, a little bump on the battery, okay, normally is the what side? Anyone know? Positive, the other side's the negative, okay, and you have to be aware of that. Now, how does this actually work? How electrons flow? Well, guess what? You know the details, party people. It's in the half reactions. What happens over here? Zinc, standalone metal, becomes what? Zinc plus 2. And how many electrons are given off? 2 electrons. What does this mean? The solid metal, which is right here, turns into a zinc plus 2. When what happens? Solid metal becomes an ion that goes into solution that water can dissolve when it gives off 2 electrons this way. So once 2 electrons are jettisoned from the what? From the anode, they travel through the wire because it's separated, and they build up on the cathode. Now what happens at the cathode? Cathode, red cat, reduction, gaining electrons. Well, the copper plus 2 already in solution says, I like those electrons. And copper plus 2, hello, gains the 2 electrons to become copper 0. Wait a minute, we're making a solid metal again. And what happens is, this electrode gets bigger. Wait a minute, on the anode side, anox, oxidation, losing electron side, the solid metal standalone oxidizes, becomes an aqueous ion, and the solid metal gets smaller. On the cathode side, red cat, gaining electron side, the Cu plus 2 jumps on those 2 electrons that came from the zinc and becomes solid. This one's increasing. You have to understand that. If I give you the overall reaction, what would it look like? It would look like this. Zinc 0 plus copper plus 2 gives me zinc plus 2 plus pure copper. We are losing solid metal, we're gaining solid metal. Now, my friends in chemistry, those are the details in this Voltaic cell. So let's set it up. So I have 0 voltage. The black lead, which is here, the black lead is going to go to the anode. So if you ever seen your folks jump their car, you notice they put the black lead to remind themselves to go to the anode, the negative side. So the anode goes to the zinc. And the positive lead, the red lead, is going to go to the cathode. And electrons are going to flow from the zinc through the voltmeter back to the cathode. And what do we have? What do we have? What's the voltage? We got a dead battery. It's not working. That's for a reason. Let me explain. The reason this battery is not working is because I need one more piece of this battery. And I want to explain it. And let me do that. Watch. There's a problem here. The problem is over time, and in fact it happens pretty fast, as every piece of zinc becomes zinc plus 2, this beaker is getting positive. So if this beaker gets positive, electrons will not go away from a positive. So this beaker gets positive instantaneously. That's why this battery is not working. What's happening over here? The copper plus ions who are in solution, who are specifically getting reduced to becoming solid copper, we're losing copper plus 2. This beaker, by losing positive, becomes negative. Electrons won't flow to a negative, and they won't leave a positive. This is getting positive as zinc plus 2 builds up. This is getting negative as I lose my positives. So we need something to keep this beaker from getting positive and keep this beaker from losing its positives, which we say goes negative. And what every battery needs a salt bridge. So here's my salt bridge. My salt bridge, okay, is nothing more than a U-tube, not a video. Okay, it's a tube that looks like a U. I have cotton in it, and what I have is salt ions. I have dissolved salt in here. I have Na plus and Cl negative. Now, before I put it in, let's draw it here. And you should draw it in too. Right now I got 0 volts. Why? Because I do not have a salt bridge. Let me draw the salt bridge. Salt bridge is going to connect the two solutions. And let me get stuff out of the way here. Bad planning on my part. Now, let me explain what's going to happen. The salt bridge, is it a pathway for electrons? Will electrons travel through the salt bridge? If the electrons could, would they go through the wire? If the electrons could pass through the salt bridge, would they go through the wire? No. Electrons are going to go through the path of least resistance. So electrons don't travel here, only ions. Now watch, very important. What do I have? I have Na plus ions and Cl negative in this case. These are ions. Now watch, party people. Who's going to travel down as I increase my zinc plus 2 over time? To combat the increase of zinc plus 2, the negative ion comes down. And to combat the what? The loss of positives, who's going to come down and relieve the positives that are lost? The Na plus. So as we lose positives, to keep this beaker from giving negative, the positives come down here. As we gain positives, to keep this from getting positive, the negatives come down. To keep, and this is important, maintain electrical neutrality. Say it with me. A salt bridge maintains electrical neutrality. Say it with me. Maintains electrical neutrality.
Excuse me, would you please send Jordan Manoy?
Maintains electrical neutrality. Jordan will come. Maintains electrical neutrality. They're going to ask you that. It keeps the beakers. Do Stop. Do electrons flow? What flows? Only the ions to keep each beaker neutral. Now, let's put it in. Right now I got no volts. It's not going to work unless I have a salt bridge that maintains electrical neutrality. Okay, and now I have a voltage. Take my salt bridge out, no voltage. Okay, there's a battery. I've put these in series. I can have a high enough voltage, a high enough force to run something. Now, let's have some fun here. Not really. Let's switch the leads. What's going to go now? What's it going now? Negative. Which negative means what? The way that I have it working, the voltmeter does not feel any charge. You just made the what? The copper the anode. According to the voltmeter, it's trying to measure a charge coming from the copper, and it's getting a negative volt. You got this messed up. Negative volt means to make this the anode, you need that energy. Why? It's not spontaneous. Copper does not naturally oxidize. Zinc does. So if you set your battery up and you get negative volts, that means it's the opposite of what it's supposed to be. My friends in chemistry, you guys have phones. When they're discharging, what's the voltage? What's the voltage? Positive. And then it runs out. Now, my friends, stay for a second, Jordan. Why would this run out? Give me a reason why this battery would die. Over time, the zinc becomes what? Zinc plus 2. What's going to happen to the solid zinc over time? It's going to go to zinc and it's going to die. When I plug my what? Rechargeable device in, I'm going to force this to be the anode. I'm going to give electricity and force the reverse to happen, and I'm going to reform the anode. That's essentially how your reversible batteries work when you recharge your phones. Come on, I'm teaching about something that's in your pocket. Okay, you're going to deal with. So it goes naturally. Your battery dies because we run out of something. It doesn't normally go back, so we force it to happen by switching the leads and adding energy to the negative volts to force it back. By the way, could I figure out the voltage in this battery? Could I figure out the voltage? Oxidation of zinc is positive 0.76. The reduction of copper is 3.6, or 3.4. You get a voltage, a maximum of 1.1 when you add the voltage. You don't have to do that anymore, but is it to your surprise that this would be positive? Does a battery work? Therefore, the voltages are positive. Okay? Homework. I would like for you to try the opposite side where it says lead to copper. I want you to identify everything that I asked for. Don't do the questions yet. I have a lecture that goes over how to do this if you're lost. But this is just an application of what we just learned already for the last week and a half. Okay? I'll post exactly the instructions tonight. Have a great day.